Have you ever seen a vinyl record? It's a large, flat, black disc covered in what looks like faint circular lines. It seems so simple, almost ancient compared to your phone. It all starts with an everyday situation that feels a bit like a magic trick. Someone carefully places the record on the turntable, lifts the tone arm, and gently lowers a tiny needle into the outermost groove. The disc begins to spin. For a moment, there's only a faint crackle. Then, music emerges, rich and warm. It doesn't come from a computer chip or a laser beam. It comes directly from the shape of the plastic itself. To understand this, we need to uncover the hidden problem that inventors had to solve over a century ago. How do you capture something invisible, like a sound wave, and store it physically? And once it's stored, how do you build a machine that can read that physical information and turn it back into the exact same sound? The answer is a journey from the microscopic to the macroscopic. Let's zoom in, way in, on the surface of the record. Those faint lines you see are actually one single continuous groove that spirals all the way from the outer edge to the center of the disc. This groove is the highway for the music. It's the path the needle will follow. But the real secret isn't the path itself, but the microscopic landscape hidden within its walls. The groove isn't smooth. If you looked at it under a powerful microscope, you would see that the walls are not straight. They wiggle and wave, full of tiny, intricate bumps and valleys. These are not random imperfections. These tiny wiggles are the sound itself. They are a physical, three-dimensional photograph of the sound waves that were created in the recording studio. When a singer sang a high note, it created a fast vibration in the air. That fast vibration was cut into the groove as a series of tight, rapid wiggles. A low note from a bass guitar created slower, wider wiggles. This is the core concept of analog recording. The shape of the groove is an analogy for the shape of the sound wave. It's a direct physical translation. So the first part of the problem was solved. Scientists and engineers figured out how to etch the vibrations of sound into a master disc, which is then used to press thousands of identical vinyl copies. This is where the record player, or turntable, comes in. And its most important component is the part that actually touches the record, the stylus. We often call it the needle, but its technical name is the stylus. It's an incredibly small, precisely shaped tip, usually made from a very hard material like diamond or sapphire. Its job is simple, yet incredibly sensitive. It must ride perfectly within the record's groove, like a train on a track, as the disc spins beneath it. As the stylus travels along the groove, it's pushed back and forth by all those tiny wiggles carved into the groove walls. It is tracing the exact same path that the original cutting needle took. If the music has a high-frequency sound, the stylus vibrates very quickly. If the music has a low-frequency sound, the stylus vibrates slowly. It is literally dancing to the shape of the sound. This is the first step of playback, converting the physical shape of the groove back into movement. The static information is now kinetic energy. It is motion. This is where the true engineering magic happens. Inside a small component at the end of the tone arm called the cartridge, the stylus is attached to the cartridge. Electromagnetic induction. If you move a magnet near a coil of wire, you generate an electrical current in the wire. The movement creates electricity. Alternatively, you can move a coil of wire near a magnet. The result is the same. It's the relative motion between the two that matters. Inside the record player's cartridge, that's exactly what's happening. The vibrating stylus is connected to either tiny magnets or tiny coils of wire. In one common design, the motion of the stylus wiggles a tiny magnet that sits nestled between two small coils of wire, one for the left audio channel and one for the right. This isn't just any random current. The electrical signal it creates is a perfect electrical copy of the stylus's vibrations. A fast vibration from a high note creates a high-frequency electrical signal. A slow vibration from a bass note creates a low-frequency signal.